Okay, onward and upward. Let's talk about orthogonal subspaces. Of course, you know what it means for two vectors to be orthogonal. It simply means that their inner product is 0. So what about two subspaces? So you say two subspaces are orthogonal if every vector from one is orthogonal to every vector from the other. So here's the definition. V is your vector space with an inner product. And we have two subspaces, W and Z. We say W is orthogonal to Z and vice versa, of course, if the following condition holds: W, Z is equal to 0 for all W in W and all Z in Z. So let's draw a picture, for example, in R3 with the dot product. Suppose you had the XY plane. The XY plane was your W, and suppose your Z was the y-axis. Excuse me, the z-axis. Then Z is a one-dimensional subspace, W is a two-dimensional subspace, and they are orthogonal. Why? Well, if you take any vector in Z and any vector in W, then they're orthogonal. Fair enough? Okay. Let's make the next definition. So here the setting is we have a vector space and W is a subspace. Then we define the orthogonal complement of W. The orthogonal complement of W is the following. It's written W perp is the following. It's the set of vectors V such that V W is equal to 0 for all W in W. So in this example with this W, what's the orthogonal complement of it? Well, it's exactly Z. In this case, W perp is Z. Okay, so suppose you have a subspace W and you have this W perp. In the previous example, we saw that W perp was a subspace. So W is a subspace. And in the previous example, W perp was a line, which was also a subspace. And of course, that's a general fact. So there are two key facts about the orthogonal complement. So one is that, so again, we're given our vector space V with an inner product, and W is a subspace. Then the first fact is that W perp is also a subspace. Okay, that's quite an important fact, and it's actually quite easy to see. And second of all, W intersect W perp is what? You tell me, what is W intersect W perp? W is a subspace, W perp's another subspace. The intersection is the set of all vectors which are in both W and its perp. And of course, you all got this. It's just the 0 vector, just a single 0 vector. And let's see why that's true. So what does it mean for W perp to be a subspace? Well, if y is in W perp and z is in W perp, I need to know that y plus z is in W perp. That's the question. If y and z are in W perp, then is y plus z necessarily in W perp? Well, let's check. What is y plus z w? That's, of course, yw plus zw. And since I'm assuming y is in W perp, this is equal to 0, since y is in W perp. And this is equal to 0 since z is in W perp. And so, indeed, this thing is equal to 0. And similarly, if c is a scalar, then cyw is equal to cyw, and that's equal to 0. And both of these are for any w in W. So this says that y plus z is orthogonal to every vector in W, and cy is orthogonal to every vector in W. Okay. So that's really elementary. And what about this second part? Why is the intersection just the 0 vector? Well, suppose W was in W, and it was also in W perp, which is to say it's in the intersection. Well, what is W inner product with W? Since W is in W, and this W is in W perp, I'm taking the inner product of a vector in W with a vector in W perp. And that must be 0. But of course, the only way that can be is if W is actually the 0 vector. So both of these are quite elementary. Okay, let's look a little more at the orthogonal complement. So we have our subspace W and the orthogonal complement W perp. And here's a simple proposition in the book. It says that every vector v in the vector space can be written uniquely in the form v is equal to W plus z, where W is some vector in W and Z is some vector in Z. And the uniquely is that W is uniquely determined and Z. There's only one W which works and there's only one Z which works. And this is quite simple, actually. So suppose this is our W and this is our W perp, and this is my vector v. Well, let's take W to be this projection. Take W to be the projection of V on W. That's basically the main point. And, well, then we know that obviously V is therefore equal to W plus V minus W. And the whole point of the orthogonal projection is that this is orthogonal to W. That's by the definition of orthogonal projection. And that is to say this vector here, which is V minus W. Well, you can really think of it as being over here, V minus W. And that is to say, obviously, V minus W is in W perp. So the answer is, given V, you take W to be the projection on W, and then you take Z to simply be V minus W. And why don't you pause for a minute here and think about uniqueness. Why is this unique? So what you need to think about is, suppose I wrote V as equal to W plus Z, but I also wrote it as W prime plus Z prime, where W and W are in W. Sorry, W and W prime are in W, and Z prime are in the orthogonal complement. Then the only way you can do that is if W is equal to W prime and Z is equal to Z prime. So why don't you pause the video and see why think if you can see why that's true. And when you are either convinced that you know or give up, come back. So what's the answer? Well, we've seen this kind of trick before. If you have this, what you do is you write W minus W prime is equal to Z prime minus Z. And the reason this is nice is that this side is in W, but the other side is in W perp, because it's a subspace. And so both of these vectors are in the intersection of W and W perp. Sorry, I'm running out of room, but I want to squeeze it in here. Let me just go up here. So then both sides are in W intersect W perp, which is 0. Remember that? And so that says that W minus W prime is equal to 0, and so W is equal to W prime. And similarly, Z is equal to Z prime. So here's another basic fact about the orthogonal complement. The dimension of subspace plus the dimension of its orthogonal complement is equal to the dimension of the whole vector space. And in fact, if suppose W has a basis W1 through WR, and suppose W perp has a basis W1 through WS, then I claim, excuse me, I need a different name for these, Y1 through YS. Then the whole set W1 through WR, Y1 through YS is a basis of V. Why is that? Well, any vector in V can be written as a vector in W plus a vector in W perp, and the vector in W can be written as a linear combination of the W's, and a vector in W perp can be written as a linear combination of the Y's. So that shows you that these vectors span, and it's straightforward to see that they're linearly independent. And if you want to see a little more about that, that's actually exercise 2.4.6. And another basic fact about the orthogonal complement is what happens if you take a vector space and its orthogonal complement and then take the orthogonal complement of that. So these are all of the vectors which are orthogonal to all of the vectors which are orthogonal to all of the vectors in W. And I think you'll convince yourself pretty quickly that taking the orthogonal complement twice gives you back the original vectors, the original subspace. The last thing I want to talk about now is some connection between the notion of orthogonality and the kernel and the range. So let's remember, suppose you have a linear map between two vector spaces, Rm and Rn, and this is given by a n by m matrix. And so remember, we have the notion of the kernel of A. That's the null space of A, or all the vectors which go to 0. And over here is the range of A. And then we talked about taking A transpose, which is an M by N matrix. So A transpose goes this way. And you can talk about the kernel of A transpose and the range of A transpose. And we had different names for these. We called this the co-range of A, and we called this the co-kernel of A. And remember, we had a basic fact about some dimensions, which is that the dimension of the kernel of A plus the dimension of the range of A transpose were equal to M. We had this a couple of weeks ago. And that's quite suggestive because look what's going on here. We have two subspaces of Rm, the kernel of A and the range of A transpose. And I'm saying that their dimensions add up to the dimension of the vector space. Well, that's a property of the orthogonal complement. So it sure looks like these two things are each other's orthogonal complements. And that, of course, is the fact. The proposition is that the range of A transpose perp is the kernel of A, and similarly the kernel of A perp is the range of A transpose. So in some sense, this is a stronger statement than this. Well, so first of all, these are the same as each other. If you take this equation and you just take the orthogonal complement to both sides, you get this one. So in any event, this is like a stronger version of this. This is just a statement about dimensions, but this is actually a statement about vector spaces being each other's orthogonal complements. But if you have this fact, if you know that the dimension of the kernel of A plus the dimension of the range of the transpose has to be the dimension of the vector space. So this statement certainly implies this.